In this session, we'll like to continue our discussion with the whole family of distributions that are called continuous probability distributions. The word continuous refers to the x-axis, the sample space, being able to contain infinitely many values, the x values, the measured values, continuously from a smaller value to a large value. So for example, just quickly by means of just showing, we look at this yellow shaded area, right, where the curve here goes from top to bottom and starts at the x value of 1 going towards infinity. Now on this graph, it is quite clear that this is so. The way we write it even without the diagram is this way, right? For x ranging from where to where. Typically, this is implied. Like for normal distribution, the bell curve, it will be from minus infinity to infinity because it's predefined. There's no way to change it. Others, like this example here, is completely arbitrary, or it arises from a very specific example, or it can be your professor's homework exercise or exam question, and that's why it's not frequently encountered. It's a bit arbitrarily constructed, so we need to then be very clear, and there's always a need to specify for what range is this continuous distribution being defined. Yeah. So outside this stated range, well, there's no more to the right of infinity, but to the left of 1, anything that's lesser than 1, we don't really say it is undefined and then stop our calculations or discussions. We typically would just think of those x values as impossible, or improbable, so improbable that it's impossible. So writing x as being undefined is to say that those values are impossible. Writing x as being defined from minus infinity to infinity, where from minus infinity until 1 and excluding 1, the PDF value is 0. And that is to say it is possible, but the probability of 0. That sounds a lot nicer, right? But it's saying the same thing. Basically, it is, for all practical purposes, treated as the same. So we're not so disturbed by questioning, what happens to those x values that are lesser than 1. So we just conveniently replace it with a probability of 0. That's as simple as that. But of course, I'm abusing the term probability a little bit because PDF is what we should be saying. All right, so this is a new term that only is defined for continuous probability distribution. So we'll come to that in a while. What are these distributions for, and why are they different from a dice distribution, like the gambling dice from 1 to 6? All these measurements, they involve a mathematical modeling of reality, such as distance, time, weight, temperature, a lot of those physical, environmental measurements, but also including businesses like money, interest rates, compound interest, return of investments, anything that's got to do with money, energy, and all their derived values like your electricity, utility, charging rates, kilowatts no, sorry, dollars or cents per kilowatts, and others like area, because it's distance times distance, right? Volume is area times distance. Speed is distance divided by time. So all these derived ratios, products, sum products or whatever of basic measurements that are continuous in nature, we tend to also use continuous probability distributions to model them. All right. So I hope here this use of the word model is, instead of confusing you further, clarifies for you to this perennially disturbing question. Why? Why must we use continuous? Isn't it true that for all these physical measures and as well as money, it's always quantized, right? It's always discrete. Like when we measure distance, there is always certain limits to our precision. Even if you use, if you drive, then your car's odometer will measure to the closest, how many? 100 meters? Because you can't tell until 100 meters has been traveled. You can't see the jump in the dial, right? The rotating dial. If you are measuring time, digital clocks will show by the seconds, so you can't see sub-seconds. Even if you use very accurate sub-seconds, microsecond digital clocks, it will be precise up to microseconds, right? You cannot see even smaller divisions of those microseconds. So how do you get continuity, isn't it? So those are important and very good questions. So whether it's weight, temperature using thermometer, money, and of course the smallest quantity of money, 1 cent. And the subdivision of it is just pure imagination, right? It exists in computer memory. Oh, you owe me half a cent. The second time you owe me half a cent, you return me 1 cent, isn't it? So it doesn't exist in real life. So why are we using continuous distributions instead of discrete distributions? So that's a very that sounds like a very basic question that shouldn't even be asked, but it's a very good question, very important question, because this why may change a whole lot of how we deal with the calculations and probabilities and statistics. So to answer this question, the quick answer is for simplicity in calculation. Okay, not for computer calculation, but for mathematical modeling, such as operating the algebra like this, performing integration, finding the cumulative probability, finding the expected value, and so on. So for modeling ease, we typically pretend, imagine that money, right? Even though the smallest quantity is 1 cent, we assume that in real life we can subdivide 1 cent to any small partition that we like 0.00001 cent is possible. Right? So we allow for that in order to achieve mathematical simplicity in the modeling. Because once that is done, a lot of interesting possibilities become available. A lot of mathematical tools become available for us to manipulate and then quickly derive some sort of insights into this um, probability distribution. Whereas if we have to insist on point by point accuracy, we choose to use discrete distributions, then we may have to settle with a kind of very unwieldy chunk of huge formulas with many subcases here and there, and it just kind of bogs down our ability to understand the simplicity of the mathematics, and it's really more a disbenefit than a benefit. All right. So I hope you get past this and feel very comfortable and logically um, very natural for us to want to use continuous distribution to model all these measurements, right? Distance, time, height, weight, money, where we realize that in real life, we can only capture these numbers, measure them with discrete precisions. So everything is discrete actually, but these measurements lend themselves readily to being modeled very nicely by continuous probability distributions. Okay, put another way, continuous probability distribution is basically a mathematical fantasy. It doesn't exist in real life, right? Nothing in real life goes to infinity or minus infinity for that matter. Nothing in real life can be subdivided infinitely many times, because I think quantum physicists will disagree, right? So nothing in real life can be subdivided infinitely many times. But in the realm of mathematics, all these are possible, right? But what do we get back when we fantasize, when we give away, reality kind of exactness? Well, what we get back is mathematical simplicity. So we can think of it as like fractions. We can cancel things out. We can perform summation, integration, calculus easily, right? I mean, you may not find it easy, but in the general scheme of things, it is easily done rather than manipulate with many cases, sub cases, and performing unwieldy summations and factorials and counting here and there, right? So that is the benefits and insights that we can glean, right, by using uh, continuous probability distributions. So I hope now you are quite convinced that this makes sense, very important, huh? And then if you are willing to welcome this continuum of measurements, right, despite our most sensitive, precise instruments of measurements, be it distance, time, weight, temperature, money, and so on. Despite that being discrete measurements, we use continuous uh, uh, random variables. So we pretend as if subdivisions indefinitely into the decimal places is possible. What do we do then? Well, then we need to describe the probability density function. Now, this might sound like a scary word, but it is necessary, and it's not scary, right? Because this is just the y-axis. Okay, just put it very simply. Think of the picture. The continuous distribution describes the continuity of the x-axis. That's right. It's no longer one number by one number, one point by one point on the x-axis. It's one continuous drawing of the pencil, if you want to go by that, right? And PDF simply refers to how tall, how high is the y value at a particular point of the x value. That's why x is a parameter, it's an input value. So we say, what is the y value at the point 1? If we are told that PDF of x is 1 over x squared, defined for x going from 1 to infinity, then at the point 1, we perform 1 over 1 square. That's 1. So the height is 1. What is the height of the graph when x is 2? So we plug in 2 and 1 over 2 square, that's 1/4. So we are going to stop at 0.25. And because it's continuous, we're going to draw a sequence of smooth curve or smooth dots joined together. And we just continue towards infinity. And the curve keeps dropping towards 0, but never quite touches 0 until it touches infinity.